Okay, hello and Assalamualaikum. Welcome to another lecture session of EPO 640 electric drive. So for this lecture session, we will be discussing on a new topic, the AC drive. So for this lecture, this will be the AC drive part 1. So for AC drive, we have the induction motor. So the induction motor, the single phase induction motor is the most frequent used motor in the world, and most appliances uses induction motors such as washing machines and refrigerators. And estimated 1/3 of all generated electricity is used on induction motors. So DC motors is in numerous applications starting to be replaced. Okay, it's starting to be replaced by this induction motor. So the advantages that you have for induction motor, such as the robustness, okay, because it has no brushes, so you have no contact on the rotor shaft. It has high power to weight ratio compared to a DC motor. Lower cost per unit power, okay, lower maintenance except for the bearings and other mechanical parts. It's easier to manufacture and has more elegant design. And in induction motors, you have NEMA classifications. So it's classified by the electrical and mechanical properties. Okay, such as, for example, NEMA design class B. So for standard locked rotor motor torques. So it's most common general purpose motor. Okay, for example, to drive fans, centrifugal pumps, machine tools. Okay, and the per unit locked rotor torque decreases as the motor size decreases. And then you have the NEMA design C, which is high starting torque motors. Okay, so it's suitable for equipments with high initial start. Okay, for example, for positive displacement pumps, okay, piston type compressors. Okay, it has high starting torque, but low starting current. High starting torque but low starting current, and it uses the double case rotor construction. And then you have the NEMA design D for high slip motors, and it's suitable for accelerating high initial loads, which take a relatively long time to reach full speed. Okay, so for example, dryers, centrifugal dryers, okay, hole punchers, oil well pumps. Okay, so it has a very high starting torque but low starting current, and uses the high rotor resistance. Okay, for example, using brass squirrel cage. Okay, and here we can see the torque to speed curve for different types of NEMA designs. Okay, so you can see for the basically for design B, you have your nominal full load torque. Okay, and you can see it increases the torque within the speed. Okay, so you have also for design C, which will cater for each particular application. Okay, so it's suitable for each particular application. And you have the you already know the principle of operation, maybe from the past lectures in machine. Okay, so you have the moving magnetic flux. So they move permanent magnet to the right, okay, at speed, okay, at speed v. Okay, and by using the Faraday law, the voltage induced is when conductor is cut by the magnetic flux within this based on this equation. So the induced voltage will produce current I, and from the Lorentz force, current in magnetic field generates the force. Okay, so the ladder will accelerate it towards the right. Okay, So that's for a linear motion. So if you wrap the ladder to form a squirrel cage, so this will form the rotor of the induction machine. Okay, so this will make it into a rotational force, rotational movement. So replace the moving permanent magnet with a rotating magnetic field. And you have your equations. Okay, you have your synchronous speed. Okay, so sometimes it's represented by ns or n syn. Okay, and the synchronous speed is the speed of the rotating magnetic field, and slip is the normalized difference between the speed of the rotating magnetic field and the speed of the rotor. So you can calculate slip with the given equation here. Okay, so for rotating magnetic field, you have, for example, you have stator terminals for A, B, C. So it's connected to a three-phase source, and the currents flowing from the line to neutral, okay, it's considered to be positive. Okay, so this will create a rotating magnetic field. Okay, so you can see that you have the sinusoidal input from each current A, B, and C. So the space within 60 or 120 degrees within each input cycle. Okay, so you can see the location of the rotating magnetic field, okay, based on each input of the current A, B, and C. And this can be further explained. Okay, so if you have number of poles also plays a role in how to determine the synchronous speed. So meaning that more poles means that you can have more poles means the speed is, you can calculate it within this equation. Okay, so the pole, okay, divided by 2, okay, is divided by the 2 pi f. Okay, and you have okay, so for this 2-pole motor, okay, for example, this 2-pole motor for a 3-phase induction motor has 3 stator phase windings. It's connected in a 3 wire Y connection. So each phase has 2 times 3 equals to 6 slots, and is shifted by 120 degrees. And the squirrel cage rotor has a short circuit bars. The motor is supplied by balanced 3-phase voltage at the terminal, and the stator 3-phase windings can also be connected in a delta configuration. So operation wise, the 3-phase stator is supplied by balanced 3-phase voltage that drives an AC magnetizing current through each phase winding, and the magnetizing current in each phase generates a pulsating AC flux. So the flux amplitude varies sinusoidally, and the direction of the flux is perpendicular to the phase winding. So the 3-phase flux generated by the phase windings are separated by 120 degrees in space and in time for a 2-pole motor. So maybe if you have a higher pole motor, so the separation is lower. Okay, the degree of separation, okay, will be lower. So the total flux in the machine is the sum of the 3 fluxes, and the summation of the 3 AC fluxes results in a rotating flux, which turns with constant speed and has a constant amplitude. Okay. So the rotating flux induces a voltage in the short circuit bars of the rotor, and this voltage drives current through the bars. So the induced voltage is proportional with the difference of the motor and synchronous speed. Consequently, the motor speed is less than the synchronous speed. Okay. So the interaction of the rotating flux and the rotor generates force. Okay. So that will drive the motor, and the force is proportional with the flux density and the rotor bar current. And the speed of the flux cutting is different between the magnetic field speed and the rotor speed. Okay. So you have two speeds can be calculated by using the radius at the rotor bar location and the rotational speed. So you can either calculate it at the radius at the rotor bar location, and this will be the at the motor, rotational speed. So the voltage and the current generation in the rotor bar requires a speed difference between the rotating field and the rotor. So consequently, the rotor speed is always less than the magnetic field speed. Okay, so obviously you will need some time to induce the rotor bar. Okay, so that's why you have slightly less speed, compared to the magnetic field speed. Okay, and actually this is defined as slip. Okay, so this is how you calculate slip. Okay, and also this will be the induced voltage at the rotor. Okay, and also you can use this calculation. So this is for a three-phase motor. So the voltage and frequency induced in the rotor depends upon the slip. Okay, slip, of course. So now we look into the construction. Construction of the induction motor. So first will be the squirrel cage rotors. So we'll look into the rotor part. Squirrel cage rotors. So this rotor has a laminated iron core with slots and mounted on a shaft, and the aluminum bars are molded in the slots, and the bars are short circuit with two end rings. So the bars are slanted on a small rotor to reduce noises. And the fins are placed on the rings that shorts the bar, and this works as a cooling system. Next will be the wound rotor. So for wound rotor, most motor uses the squirrel cage rotor because of the robustness and the maintenance-free construction. But for larger models, for large and older motors, it uses the wound rotor with three-phase windings, placed on the rotor slots, and the windings are connected in a three-wire Y connection. So the ends of the windings are connected to 3 slip rings. And resistors or power supplies are connected to the slip rings through brushes for reduction of starting current and for speed control. And you can see the diagram for the wound rotor. So the lock rotor current. So why do we need wound rotor when we have a squirrel cage? So this is a previous maybe for larger load torque. So the lock rotor current can drastically reduced. So you have a lock rotor current can be reduced by inserting 3 external resistors in series with the rotor. and the speed can be varied by varying the external rotor resistance. So lock rotor current usually will happen for big torque loads. Okay, so sometimes it's a problem for this for bigger machines, okay, bigger load, and this can solve the problem. So the motor is ideally suited to accelerate high initial loads, okay, and it requires a long time to bring up to speed. Okay. So next we look into the equivalent circuit of the induction motor. So how we model the equivalent circuit, we do the equivalent circuit. We can say that the motor is similar with a transformer. Okay. So usually we model the equivalent circuit of the motor to a transformer. Okay. So transformer, you have your consists of three parts. You have your primary winding, secondary winding, and the core, or the magnetic core, where the magnetic flux is transferred. So you have this segment, okay, 1, 2, 3, and 4 terminal. So the core resistance for R1, okay, R1, and for R2, so this will be the coil resistance. So it's a finite resistance in the stator and the rotor windings. Okay, so we represent it as R1 and R2, and then you have XM, so magnetizing reactance XM. So when 3 and 4, if it's open, okay, so there is no load magnetizing current drawn from the supply due to self-inductance. So this is modeled with the inductance, okay, inductive branch, and we put it as XM, okay, magnetizing reactance. So then we look into the core losses, okay, RC. So RC is the core losses is represented by RC. So it's a pulsating flux induced, okay, eddy current and hysteresis losses in the core. So it can be both. So although they are doing lamination, but you still have you still can calculate the eddy current losses. So the losses can be modeled, okay, by RC. Okay, we model it using RC in the circuit, whereas the losses is I C power to 2 times RC. So the core is laminated. Okay, usually it's laminated to reduce eddy current. And then you have leakage reactance, reactance X1 and X2. Okay, X1, X2. Leakage reactance. So in practice, there will be leakage flux, as some of the flux will exit, okay, outside the core, and it's modeled as a leakage leakage inductance. Okay, so for L1 and L2, and for stator and the rotor respectively. So leakage reactance X1 and X2 are then given by this equation. And then from here you can also calculate the induced voltage, okay, so for V1 and also for the frequency F2. Okay, so for V1, okay, so V2 is S, okay, slip times N1 and N2 out of N1 ratio, okay, ratio N2 to N1 times V1, V input, V in, okay, sorry, V1, okay, not input, and then you have your frequency F2 equivalent to slip times F1. So the flux rotates with the synchronous speed and the rotor with the motor speed. Okay, so consequently the flux cuts the rotor conductors with the speed difference between the rotating flux and the rotor, and thus as we have discussed before, So the speed difference is calculating using slip equation. Okay, so the induced voltage is within this equation. And you have the division of the rotor and stator induced voltage, okay, within this equation. And the speed difference determines the frequency of the rotor current, okay, frequency within this equation. So the rotor, okay, the rotor circuit leakage reactance is this equation. So this is the induction motor equivalent circuit. Okay, so from there we can represent it with, okay, voltage and current, okay, within this equation. Okay, and so since this is what you call it, some things quite open, complicated, when you connect it to the load. Okay, so should be the next modification is to insert separate, okay, to the referred motor resistance, okay, into two components. Okay, and with this you can okay, so this will be represented by the effects of the copper loss. Okay, and you have also losses, okay, on the outgoing mechanical power. Okay, sorry, this is not loss, but this will represent the outgoing mechanical power. Okay, so this model is actually is inconvenient for analysis due to the to get the RC and XM shunt branches, the value of that. So what we do is we do assumptions, okay, to make the analysis more simple. And there are two ways to do it. You have the approximate, okay, equivalent circuit, and also you can use the IEEE recommend equivalent circuit. So for the first assumption is if the voltage drop across R1 and X1 is small enough, we can say that E is more often equal to V1. Okay, so therefore the magnetizing branch can be removed to the machine terminal, and this is acceptable for motors that is above 2 HP. So from there we can, this will be the voltage and also the current equation. Okay, so next is the IEEE recommended equivalent circuit. So the assumption is that, so the sum of the core losses, friction losses, and windage losses is relatively constant and can be lumped together as the rotational losses. Okay, so then, okay, RC can be removed from the equation. Okay, and the leakage X1 is relatively high, thus the magnetizing branch cannot be moved. Okay, so that's for the IEEE equivalent circuit. Then we look into the power flow per phase. So for power in, this will be the calculation for power in, and then you have core losses. It will go to the rotor copper losses. Okay, and then you have this air gap calculation. Okay, so power in the air gap. Okay, and then the power at the power developed or the power out. Okay, so for there they will go through some of the losses, and the losses we can look into the power flow. Okay, so the induction motor performance is evaluated using the equivalent circuit, and you have your power flow diagram. Okay, so from P in, so minus all the losses, stator copper losses, rotor copper losses, mechanical losses, okay, stray losses. So then you have the output. Okay, so the torque speed relation is calculated from the equivalent circuit. Okay, and then this will be the Okay, electric power, the developed power is within this equation. So this will be all the equations how to calculate. Okay, so on the torque speed characteristic, the air gap power, okay, the synchronous speed, okay, the torque, okay, output power, and so on. Okay, and you can do additional further readings within the textbook stated here. Okay, so that's all from me for today. Thank you and have a nice day.